Welcome. Thank you for joining us for today's webinar, Phase Change Material Heat Sinks, Fundamentals of Operation and Real-World Applications, presented by Advanced Cooling Technologies and TechBriefs Media. I'm Bruce Bennett, editor at TechBriefs Media, and I'll be your moderator today. This webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation. Participants will receive a follow-up email with instructions for downloading the presentation and viewing the archived version of the webinar. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce today's speakers, Pete Ritt, ACT's Vice President of Sales and Marketing, and Jens Weyen, Lead Product Development Engineer for ACT's Electronics Products Group. Mr. Ritt joined ACT in 2010 to head their technical services business. During this time, the group has successfully provided thermal consulting, design, and prototyping solutions to commercial customers in the lighting, renewable energy, industrial equipment, and medical industries. Throughout his career, Mr. Ritt has successfully managed numerous new technology projects in a variety of industries. He is a former RCA executive where he was responsible for developing technologies and products for commercialization in the consumer electronics industry. He also commercialized household good products while an executive at Woodstream Corp. He has been granted over 20 patents and holds degrees in chemical engineering from the University of Notre Dame and an MBA from Shippensburg University. Mr. Weyen has gained 5 years of research experience through his studies and time spent at Advanced Cooling Technologies. During his time at ACT, he has contributed to thermal solutions for radar, power electronics, rotating equipment, and other high-power electronics, many of which include heat pipe embedded solutions. He has served as PI on several SBIR programs, including a DARPA Phase 1 and 2 funded program focused on passivation of laser diode microchannel coolers, a DOE Phase 1 and 2 funded program on passivation coatings for high-power RF loads, and an Army Phase 1 funded program to develop a liquid cold spray system. Now that you're familiar with our speakers' qualifications, I would like to turn the program over to Mr. Ritt.
Thank you, Bruce. I'm Pete Ritt, along with Jens Weyen. We are delighted to be with you today. Devices with increasing power, smaller footprints, and greater mobility are demanding a good, stable, cost-effective thermal management solution, and many options are available today. In today's webinar, we'll explore one technology that is experiencing tremendous growth in a variety of military and industrial applications, temporary thermal storage / phase change materials, also known as PCM. The most common solution from this platform is the PCM Heat Sink. The goal of this webinar is to provide viewers with an understanding of PCM, including some aspects of the design that need to be explored when investigating potential PCM solutions. We'll start today's webinar with a general overview of phase change material, including how it functions, common PCMs, and key material properties. From there, we'll explore critical design considerations such as fin volume and void allocations. And finally, we'll review real-world examples of both standalone PCM heat sinks and higher power PCM heat exchangers. As is probably obvious by the name, PCM operates using a phase change, in most cases solid to liquid phase transition. During the phase transition, a material's latent heat increases dramatically, which allows it to store thermal energy for a finite period of time. The major benefit of integrating PCM is that it will maintain its melting temperature during the phase transition. Depending on how much PCM is in the system and the power being applied to it, the heat sink storage capacity can be a couple of seconds to several minutes to even a few hours. The key attribute of phase change materials is the latent heat of fusion, which is the heat or energy that is absorbed by a material during the melting process. phase change materials typically can absorb orders of magnitude more heat than a single phase material. The graph on the right helps to explain this effect. Temperature is plotted on one axis, heat, Q, is plotted on the other. The red line is a plot of sensible heat, that being heat that causes a direct temperature increase. The blue line shows the performance of a phase change material. When the PCM reaches its melting point, it maintains a constant temperature, as seen in the blue shaded area. It maintains that temperature until all of the PCM is melted, when it will return to the sensible heat regime. Note the sharp temperature transition is a function of PCM purity. This effect has many benefits, the most important of which is temporary heat storage. These solutions can help reduce weight of large metal heat sinks, are compatible with many common materials, function reliably over many heating cooling cycles, and is completely passive, requiring no moving parts. Some challenges that need to be addressed are the very low thermal conductivity of these materials and the relatively high cost of high purity, long chain hydrocarbons. Lower cost, lower purity materials are also available. In designing a PCM heat sink, of course, a critical parameter is the selection of the PCM itself. The key attribute is selection of a PCM that has a melting point at the temperature that is acceptable for the device operation. You can see on the chart on the right a series of materials and temperature ranges from plus ice. Several options are available. Other important parameters include compatibility with the base heat sink material, the type of PCM, its purity, and heat storage capacity. Once potential materials have been identified, they should be evaluated for storage capacity, including fin thickness, required PCM volume, and weight. In the table at the bottom, for example, 3 PCMs with the same melting point and fin volume deliver different heat storage performance due to different latent heat and mass properties. There are several factors that need to be considered when selecting a phase change material. An ideal PCM will have a high heat diffusion, high thermal conductivity, high specific heat and density, long-term reliability during repeated cycles, and dependable freezing behavior. In this chart, green indicates attractive features and red indicates challenges. There are several classes of phase change materials. Paraffin waxes are the most common PCM because they have a higher heat diffusion per unit weight, have a large melting point selection, provide dependable cycling, and are non-corrosive and chemically inert. When designing with paraffin PCM, void management is important due to the volume change from solid to liquid. Paraffin PCMs also have low thermal conductivity, so designing a sufficient conduction path is another key design consideration. Hydrated salts are another category. These PCMs have a high heat diffusion per unit weight and volume, have a relatively high thermal conductivity for nonmetals, and show small volume changes between solid and liquid phases. They are less commonly used since they are corrosive and long-term reliability is uncertain. Other PCM materials such as metallics, non-paraffin organics, and liquid-to-gas phase change materials are available but tend to be used less for these applications. As mentioned, paraffin waxes are the most common PCM. They are chemically compatible with most metals. They have large latent heat and can be obtained over a wide temperature range. The table at the bottom shows some high-purity paraffin waxes used in many electronics applications. Temperature ranges of 72 to 76, 66 to 70, and 59 to 66 degrees C are good to ensure safe operation of many electronic devices. As we saw previously, many other PCM choices are also available. At this time, we'll turn it back to Bruce for a polling question.
So it didn't go. Who does your company use to resolve critical thermal management issues? In-house resources, external experts? D, C, combination of both in-house and external resources? D, not sure. Please take a moment to give us your answer, and we'll return to the presentation in a minute. Okay, Pete, I think you can continue.
Thank you, Bruce. In the next section, we will look into design considerations for PCM heat sink modules. These modules are sealed, leak-tight units, and the internal design is critical to operation. In this section, we'll touch on optimizing the fins for proper melting of the PCM and void and pressure considerations. We'll also provide a comparison of actual tested PCM modules. In the first step of the design, power and thermal storage time targets are used to determine the volume of PCM required. From there, two primary challenges arise associated with the design of a PCM module. The first is designing around the poor thermal conductivity of PCM. Wax-based PCM have thermal conductivities between 0.2 and 0.3 watt per meter degree Kelvin. Simply filling a container with PCM and applying a heat load would create a large temperature rise as the PCM melts. The second challenge is managing voids at the location of critical heat loads. You can see in the figure on the right, a void volume is present to allow for expansion of the PCM during phase transition. In most cases where orientation with respect to gravity varies, the location of the PCM when it melts and freezes will vary as well. If there is a significant empty space around the critical component, that component can see a large temperature rise before the PCM absorbs the heat load. The solution to both of these challenges is in the design of the internal conduction paths, which typically are fins internal to the heat sink. As you can see by the thermal resistant network outlined in the figure, conduction will play a large role in ensuring the PCM melts without significant temperature rise. The fin spacing, or fin pitch and thickness of the fins, are critical design considerations, and the next slide will demonstrate the trade considerations during the design. Since most PCM heat sinks are paraffin-based, getting the heat into the PCM efficiently is a key design parameter. Here is a plot that can be used to identify a starting point for fin pitch and thickness within a PCM heat sink. The solid line shows time to melt, or thermal storage, for a given power on the left axis. The matching colored dashed line is the corresponding thermal gradient through the fin and PCM shown on the right axis. Both curves are a function of fin spacing. As you can see, there is a trade-off between thermal storage capacity and delta T. As you add more fins, you reduce your thermal gradient, but displace more PCM, which reduces thermal storage. A scenario with too few fins is shown towards the left side of the plot. At the other extreme, the spacing between the fins is large to maximize the volume of PCM, but thermal gradients are large due to the poor conductivity of the PCM. This occurs towards the right side of the plot. For the heat load and geometry used to generate these curves, the optimum fin spacing is between 0.05 to 0.1 inches. This is where marginal gain in the thermal storage capacity are observed as fin pitch is increased. Optimizing fin pitch and thickness assures that all PCM is melted with a minimal thermal gradient, thereby maximizing the performance of the heat sink. A schematic of the PCM heat sink module structure is seen on the right. Internal features include PCM, fin structure, and void allocation. During manufacturing, a heat sink module will be completely leak-tight, which makes it a pressure vessel. As we touched on before, since there is expansion going from a solid to liquid, the unit requires a void volume when in the solid state, typically between 8 to 15%. One of the challenges is assuring the void volume does not cause unwanted temperature rise, and fortunately, this design challenge is resolved by proper fin design that we discussed in the last slide. Since the fins will provide a good conduction path to get heat into the PCM, the temperature rise is minimal, no matter if there is a small void at the large heat-generating component. When dealing with high heat fluxes in discrete location, management of molten PCM flow must also be considered in the design. Localized heat input can produce high pressure gradients as PCM melts, expands, and yields the surrounding solid PCM. Enhancing heat spreading with heat pipes, for example, can reduce this effect by uniformly melting the PCM. Flow configurations that allow the PCM to move easily during the melting have also been developed. Here is an example of a typical PCM application. In this case, after selecting the PCM, determining the required volume, and designing the enclosure with proper fin and wall structure, it's time to manufacture and test the PCM. This slide shows a tested sample with the estimated properties shown to the left. Note the large changes in specific heat for the different temperatures. Specific heat, which is related to the latent heat of fusion mentioned previously, is the amount of heat per unit mass required to raise the temperature of a material by 1 degree C. The reason why PCMs are so effective is that during phase transition, there is a dramatic increase in specific heat. As you can see, there is a large order of magnitude increase from approximately 1,600 joule per kilogram degree Kelvin as a solid to over 60,000 at its melting temperature between 72.2 and 75.9 degrees Celsius. Here are the results from the test setup we saw on the previous page. As indicated by the solid black line at the top of this graph, we applied slightly over 40 watts of total power with air at room temperature. If you're familiar with PCM, you've probably seen the blue theoretical line. Basically, the module heats up until it reaches the PCM melt temperature. It can then hold within a few degrees of that temperature until nearly 100% of the PCM has melted. Once all the PCM is melted, the temperature begins to rise at the rate dictated by the specific heat. In this case, the PCM heat sink was designed to absorb the heat load for about 250 seconds with some margin. The red tested results match fairly well, and the theoretical temperature was never exceeded. And now we'll turn it back to Bruce for our final polling question.
Thank you, Pete. For our second polling question today, we'd like to know, are you facing any thermal management issues in the next A, 0 to 6 months, B, 6 to 24 months, or C, no immediate issues? Please take a moment to answer that question. Okay, Pete, please continue.
Thanks, Bruce. Next, we'll look at some real-world examples of where PCM are being beneficially used. We'll look at relatively low-power application where PCM is being used for on-chip pulse power. Then we'll look at a typical application for electronics cooling. And finally, we'll look at a different application, PCM Heat Exchangers, where the PCM is part of a 3-circuit system, which is used to reduce the overall size of a very large device. First, we'll start with on-chip PCM. Many semiconductor communication devices operate in a transient on-off mode. During the on cycle, they utilize a lot of power, and the devices can get quite hot. Fortunately, duty cycles are relatively short, typically between 2 and 10%. Locating PCM near the individual gates can aid in increasing performance reliability and extending life of these devices. As can be seen in the schematic on the right, the pulsed heat source is on a gallium nitride layer and a silicon substrate. PCM is embedded within the silicon substrate, and when the device is on, the heat will cause the PCM to melt. As we have seen, the melting provides some stability in temperature, and so very high temperatures from repeat cycles are avoided. In these applications, ensuring the proper amount of PCM, enough to absorb all of the heat during the on cycle, while also being able to dissipate all of the heat in the off cycle, is important. Part of the system design should include calculations of the minimum distance between the heat source and the PCM to avoid parasitic effects. Here are some results. The high junction temperature during the on cycle is the biggest challenge in these pulse devices. As you can see in the graphs at the bottom left, the objective in adding the PCM is to limit the temperature rise of the high electron mobility transistor, HEMT, to the PCM melt temperature. The picture in the center is an application of this approach, where the PCM is located within grooves that are sealed with an indium layer. The graph on the lower right plots the normalized drain current versus pulse width. You can see with much more stable performance the PCM provides, especially at high pulse widths. Our second application is heat sinks for electronics thermal management. An exploded view of these types of heat sinks is seen on the right. The red metal parts encompass the enclosure in which the PCM and folded fin assembly are located. The design process block diagrams detail the key individual steps. First, the transient heat load power plus time is established. This determines the required PCM reservoir sizing. There is then the iterative design sequence reviewing fin design and overall structural analysis that ultimately results in the final design. This transient thermal modeling will confirm the heat transfer to and from the PCM, identify the location of the PCM melt front over time to ensure adequate PCM is present to handle the full transient load and the overall system delta T to make sure the device are not overheating. Let's look at some results with this kind of design. Here are the results. In the graph on the right, the dotted red line represents the heat load profile. The heat load is on at the beginning of the graph and drops down at approximately 200 seconds into the cycle. The blue line represents the PCM heat sink temperature, and the black represent the ambient temperature the devices experience. One can see through the varying heat loads of the dotted red line, the blue PCM remain relatively constant and at a slightly higher temperature than ambient. The relative rise of the blue PCM at the end of the graph is an indication that all of the PCM has melted and could be in a runaway condition. Fortunately, in this case, the on cycle is ended and the PCM will begin dissipating heat. On the right is a schematic of a melt front for a single folded fin. The red heat source is on top, and the melt front, that is the edge of where the PCM is undergoing the solid to liquid phase transition, is located at the yellow to green color transition. It is, of course, important that the melt front move reliably through the PCM heat sink to ensure that there are no unwanted hotspots. In our final example, we would like to step beyond the PCM heat sink and consider a PCM heat exchanger. Like with the heat sink, addition of PCM can enable sizing of the heat exchanger to be based on the average power rather than the peak power. The concept here is that the PCM exchanges heat with both a heat source and a cooling loop that is tied directly to the ultimate heat sink. PCM temporarily stores the thermal energy and slowly releases it to the ultimate heat sink. The ultimate heat sink can then be reduced in size and weight regardless of what type of system. Some examples include reducing radiator size in space applications and reducing convection heat sink volume in terrestrial ones. In this example, we'll show the effect of a fluid heat exchanger that couples a liquid cooling system with a vapor compression system. This specific application is a heat exchanger for directed energy weapons, but is applicable anywhere that a significant pulse mode operation is present. In this case, operation is typically less than 40%, which allows for mass reduction in the entire system. The schematic in the bottom right corner represents a sample directed energy weapon system. Here, the high energy lasers, HEL, were cooled with a deionized water loop, which is depicted in the bottom of the schematic on the lower right. The vapor compression loop, seen at the top of the schematic, is where the heat is ultimately rejected during the off times with an air-cooled condenser. The PCM heat exchanger couples and transfers the heat between the cooling loops, while also dampening the pulse from the high-energy lasers. The design considerations for this system are similar to heat sink modules, where one must determine the volume of PCM required to absorb the power over the duty cycle and then design the system with enough PCM surface contact in order to reduce conduction gradients through the PCM. Here is a schematic of a cycle using a 3-circuit heat exchanger. At the beginning of an on cycle on the right-hand side, the hot DI water coolant, PCM, and cold vapor compression system are in equilibrium. The high-energy laser is turned on, the temperature of the hot coolant increases, the PCM absorbs the heat and begins to melt. At the end of the cycle on the left, the cold vapor compression loop is taking heat away, causing the PCM to freeze or solidify. When the on cycle ends, the hot coolant temperature is reduced, and the cold cooling loop causes the PCM to freeze, soon ready to initiate another cycle. More specifically, the PCM heat exchanger can accomplish this goal by having thin layers of PCM sandwiched in between parallel flows of both the deionized water and the refrigerant. The vapor compression system operates continuously but is only sized for the average load, since the PCM balances the peak load from the DI water loop. These layers can be added as needed depending on the PCM volume requirements. So what's the benefit? ACT determined the performance difference for a system operating around a 33% duty cycle with and without a PCM circuit. This analysis used off-the-shelf components outside of the PCM heat exchanger. As you can see on the table on the bottom right, the weight of the compressor and condenser are significantly reduced. And although additional weight of the PCM and enclosure mass to the heat exchanger portion was included, there is an overall weight reduction of 54%, which is quite significant. Thank you for joining us today for this webinar on phase change material. The key takeaways we hope you learn is that phase change material heat sinks can be used as an effective way to temporarily store thermal energy. This technology has many benefits, including a totally passive solution, redundant thermal management, as well as the opportunity to reduce the overall size of your heat sink or heat exchanger. We reviewed some of the basic PCM material and heat sink design considerations. PCM selection and volume is dependent on the component operating and boundary conditions, primarily power and time. These parameters are well known and can be determined quite accurately for those skilled in the art. Also, the internal design of the system is critical to their performance. The two important design considerations are proper conduction path to and from the PCM to address the poor thermal conductivity of the PCM itself, and designing the module for appropriate internal pressure. Again, those issues are well known and can be addressed. Finally, we provided 3 specific examples of using PCM for temporary thermal storage, all with different thermal storage requirements. We discussed applications requiring very low power on-chip devices, medium power electronics cooling, and high power heat exchangers for directed energy weapons. Undoubtedly, there are many more, and fortunately, with the growing acceptance of this solution, there is also a growing expertise into how to implement them. Thanks again for your time, and now we'll turn it back to Bruce for some of your questions.
Thank you, Pete, for that most informative presentation. Now, if you're ready, Jens, we'll get to the question and answer part of the program. First question. What are the key application requirements that make PCM heat sinks a good option?
Sure, that's a good question. The main design requirement that suggests a PCM solution would be helpful is when you have a high transient heat load or a temporary heat load. The PCM allows you to store energy for a while and dissipate it when the heat load is off. This allows designers to design their ultimate heat sink for a time average heat load as opposed to the peak heat load. But it also comes in handy when there's a one-time use application or you need some backup thermal storage.
Thank you. Second question, is there a guideline for how much additional volume needs to be allocated to compensate for the solid to liquid phase transition?
There is. It depends somewhat on the PCM that you're using, but generally there's about an 8 to 15% change in volume between the solid and liquid phase. You may want to add some extra volume for the void just for some safety margin.
Can paraffin waxes go lower than the temp ranges shown?
They can. So a lot of the paraffin, well, all the paraffin melt temperatures are a function of their molecule length, and you can get chains varying in length that vary the temperature from below 10 C to above 75 C. So quite a range and a lot of options within that range.
Have you already used heat pipes as fins in real applications?
We have. So the driving factor for selecting the fin is the overall fin efficiency. So when you do the modeling and get an idea of the overall thermal resistance network, if you're paying a high fin efficiency penalty, you would want to make the transition from a solid metal like copper or aluminum to a higher performance fin such as a heat pipe.
Thank you. I'm afraid that's all the time we have today. I'd like to thank Mr. Ritt and Mr. Wayant for giving us such an informative presentation, and I'd like to thank today's attendees for participating. That concludes today's webinar sponsored by Advanced Cooling Technologies and TechBriefs Media.